Okay, so let's continue on to objective 3, and that's going to be to find products and quotients. So you're going to see more about the usefulness of the polar form. So we're going to find products and quotients of complex numbers in polar form. So we have a theorem that tells us how to do this. So it says if I have a complex number 1 that has a modulus of 1 and argument theta 1, and I have a second complex number that has a different modulus and a different argument, so those are two distinct complex numbers, then if I want to multiply them together, turns out that I multiply the moduli, so multiply moduli, that's the plural of modulus, multiply moduli. Oh, and look what happens to the angles. Add angles. So I find this a useful mnemonic device. Multiply, moduli, add angles. And we'll show why this is true in a minute. And then as long as the second complex number is not the number 0, then you can find the quotient by finding the quotient of the moduli and the difference of the angles. Now this theta, remember, always needs to be between 0 and 2 pi. So if when you add or subtract, you're not in that range, you need to adjust and give the angle its name, that is between 0 and 2 pi. So here's the proof of the product formula. Notice that if we have z1, which is r1 cos 1 plus I sine theta 1, that's z1, and we multiply it by r2 cos theta 2 plus I sine theta 2. So we bring the r1 and the r2 out in the front, and then you get cos theta 1, cos theta 2, so I'm foiling now, plus I cos theta 1 sine theta 2, plus I times sine theta 1 cos theta 2, and then plus I squared, which is minus sine theta 1 sine theta 2. So let's look at this and see if we recognize this. So I have the r1, r2. I'm going to just rearrange a little bit and have cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. So think about whether you're recognizing that. Plus I, factor out the I, and get cos theta 1 sine theta 2 plus sine theta 1 cos theta 2. So think about the sum and difference formulas that you learned, and here you have cosine, cosine, sine, sine with a minus. This is the cosine of theta 1 plus theta 2. It's the cosine of the sum of two angles. Plus I times, and here I have sine, cosine, cosine, sine, so I have the sine of the sum of the two angles. And so now we've proved that if you take two complex numbers and multiply them together, the result has a modulus that is the product of the two moduli and an argument that is the sum of the two arguments. So you multiply magnitudes, add arguments. So we'll do some practice of these together. Notice that they have to be in polar form to begin with. So chances are good that on the next test, I will give you the number in rectangular form, have you convert it to polar form, and then do the product and the quotient. Okay, so the last part is really the point of why we're doing all this. De Moivre's theorem allows us to find powers and roots of complex numbers much more quickly than if they're in rectangular form. So remember that if z is written in polar form as r, sorry about the flipping around, r cos theta plus I sine theta, then it turns out that if you take it to a power, if you think about it, that's just successive multiplying. So if you had z squared, it would be r times r cosine of theta plus theta plus I sine theta plus theta oh, that's r squared cosine of 2 theta plus I sine 2 theta. So do you see where the formula comes from? It says multiply the theta by whatever this power is. And then r is to that same power because you've just multiplied it by itself over and over again, however many times the number n is. So remember that taking something to a power is really just successive multiplication. That's the meaning of the exponent. So the proof of this is a little beyond our skills, but you can learn it later if you need the proof. So first, we're going to write each expression in this. We're going to end up by writing the standard form, but here we have a complex number written in polar form. It's to the power of 3. And so we'll work on these examples together in class. And notice that you have to be written in polar form to use de Moivre's theorem. So here's a couple of exercises where the first step is going to be write the number in polar form and then use de Moivre's theorem. And hopefully you can see the usefulness of this, because if you want to do root 3 minus I to the 6th the long hard way, oh my gosh, this is going to take way too long. And I have so many chances to make mistakes. So it's going to be much easier. And the higher the power, the easier it's going to be to use de Moivre's theorem rather than doing it the old hard way. So the last thing we're going to do is find complex roots. So find complex roots. And if you have that z to the n is w, then z is called a complex root of w. So for every complex number, it has 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, and so on. So for every complex number, you can find 5 fifth roots. So this is not the case for strictly real numbers that you've looked at before, right? Because you would have said, well, let's see, the cube root of 27 is just 3. Oh, well, it turns out that when you allow complex numbers, there's actually 3 cube roots and not just this one real one. So to find all of the roots, we're going to have a formula that I would give you this formula and expect you to know how to use it. So let's take some time to analyze the formula. So I have this complex number, w, that's given to me. It's given to me with an r that I know, so that's the modulus or magnitude. And I have a given argument, theta sub 0. So theta sub 0 is the argument of the given complex number. Okay, then k is a counter. Okay, so theta 0 never changes. Doesn't change. It's what you were given in the problem. N is also not going to change because n is the number of roots you're looking for. So if it's cube roots, n is 3. If it's fourth roots, n equals 4, and so on. So n is also fixed in a given problem. It's not going to change for each root. The thing that changes is the k. So see how there's a k subscript here. This k corresponds to this k here and this k here. So theta 0 over n is the same in every root. That part's the same and doesn't change. And the nth root of r is the same in every root. So n doesn't change. Theta sub 0 doesn't change. The thing that changes is the k. So if we were doing cube roots, for example, we'd say z sub, and notice it starts at 0. So you start at 0. So we'd say z sub 0 is the nth root of r, which is the cube root, and then it's the cosine of whatever your theta sub 0 is over 3, that's the n, plus nothing because the k is 0, plus I sine theta sub 0 over n plus nothing because the k is 0. So this is the first cube root. Okay, so then we would let the k click up by 1 and say, okay, now we want to find the next cube root. So it's always going to be cube root of r. That part doesn't change. Cosine of theta 0 over 3, that part doesn't change. But now k is 1, so it's going to be 2 pi over 3. The n doesn't change. Plus I sine theta 0 over 3, this should be a 3, sorry, plus 2 pi over 3. So wherever the first root's angle was, theta sub 0 over 3, the next one is going to be 2 pi over 3 farther around. Then how many cube roots do we have? 3. So here's the first cube root, the second cube root, and the third cube root. So we stop after this because you'll just get a repeat. You won't get another new one. So we have cosine of theta 0 over 3 plus, now k is 2. Here's the k. So now it's going to be 4 pi over 3 plus I sine theta sub 0 over 3 plus 4 pi over 3. So wherever the first angle was, suppose the first angle was at pi over 3. So suppose theta 0 over 3 was pi over 3. Then the next root is going to be at 2 pi over, you're going to add 2 pi over 3 to that, so it's going to be here. And then you're going to add 4 pi over 3 to the first one. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. I don't think I did that right. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. Here's going to be the third cube root. So do you notice anything about them? 360 degrees is all the way around the circle. Cube roots mean you're finding 3 of them, so they're 120 degrees apart. This is always going to happen with cube roots. Wherever the first one is, the other 2 will be evenly distributed. And if you have fourth roots, the picture will always look like this, where your fourth roots will each be 90 degrees away from each other because 360 degrees divided by 4 is 90 degrees. So if you have fifth roots, how far apart from each other are they going to be? 72 degrees. So they'll be evenly spread out, 72 degrees apart. Okay, so we'll do lots of practice with that until you become proficient.